Okay, so let's discuss some special cases in transportation problem. Okay, firstly that we will be discussing maximization type. Transportation problem. Secondly, we will be discussing some constraint transportation problem. And what are the constraints we are considering is that suppose there is no transportation from say source I to destination J for some I and J. Okay, and secondly, source I, say SI, transport some fixed amount to destination J, that is TJ. And third, source I, SI, transport at least say alpha units to destination J, that is TJ. So if these conditions are given, how will we solve the transportation problem? Okay, so first case is the maximization transportation. Maximization type transportation problem. See, so far we have discussed the formulation for minimization transportation problem. In case of maximization transportation problem, just as in linear case, you just have to consider that Zij minus Cij is greater than or equal to 0 for optimality. So if Zij minusCij's are greater than or equal to 0 for all Ij, then we say the solution is optimum for the maximization transportation problem. But if Zij minusCij's are not greater than or equal to 0, that is sum of Zij minus Cij is negative. So in this case, if Zij minus Cij is less than 0 for some Ij or maybe more than one Ij, so then what you do, we select the most negative Zij minus Cij to enter into the basis, and then again the minimum ratio rule is followed. That means you have to select for leaving criteria, you have to choose that cell where you get the minimum of the negatively marked cell. Okay, so leaving criteria is safe. Leaving criteria is same. So that means if somehow we have this kind of situation, say it's 2 across 3 transportation problem, 3 4 5 3 2 6, and suppose you are transporting 20 30 say 20 and say 40 units. So this is one of your basic feasible solution, and say Zij minus Cij is minus 7 here and 5 here. So what you are going to do in this case, you will be selecting the most negative Zij minus Cij. So you will select this one, and then you enter this cell 1 3 into the basis, construct a loop. Okay, mark positive, negative alternatively. Okay, then out of the negatively marked cells, you select the minimum. So minimum of 30 and 40, if you select, so it is 30. So that means this cell will go out of the basis. Okay, this will go out of the basis and this will enter into the basis. And in that case, your new solution will come out to be what? This. So overall, the problem is same. Transportation structure is same. It's same to the linear programming case as in case of minimization and maximization cases. The entering and the leaving criteria changes. Okay, so it all depends upon the ZJ minus CJ. So leaving criteria essentially remain same because we are taking care of the minimum ratio rule. Here, the minimum of the negatively marked cell is considered, but the entering criteria will be changed. So for maximization case, your most negative ZJ minus EJ enters, and in case of minimization problem, most positive ZJ minus EJ enters. So in this case, your new basic feasible solution will become what? 30 here. Now this cell leave out of the basis, and then you have 50 here, and then 10 here. Other is 20. So this is 3, 4, 5, 3, 2, 6 are my cost. So this is my new BFS. Okay, so this is the um, transformation or the operation you have to consider while you are solving the maximization type transportation problem. Okay, rest of the things remain same. So next is my constraint cases for the transportation problem. Okay, so first of that case is that um, the constraint cases. Okay. Okay, so my first case is what happens when source I does not transport anything to destination J. Okay, that is DJ. So consider a case here. So what happens in this case? Suppose this is a transportation problem with two sources and three destinations: source 1, source 2, destination 1, destination 2, destination 3. And suppose usually I have given some cost 3, 4, 9, 1, 7, 2. Okay, and say this is the amount available. I have 10, 20, and this is the requirement. Simply, I am talking about the balanced transportation problem. Now, suppose you are given the condition that source 1, okay, source 1 supplies nothing uh, or does not transport anything to destination 3. Okay, so that means there should be no transportation from source 1 to destination 3. How we can take this thing into account? So in this case, the cost of C13 cell, okay, because from source 1 to destination 3, we will change this cost to M. So what we are going to do here is you put, instead of 9, okay, you remove it and you put capital M here. So where capital M is a very large number, just as in case of pick M method. Okay, so what will happen in this case? Suppose you are now when you are using the least cost method or the northwest corner rule, you won't be able to transport anything here. Suppose in case you are able to give initially some amount to this cell where you are given a M cost, eventually when you are using UI VJ rule, so this, because of this M, your Zij minus Cij will be very large for this case, and so it will eventually go out of the basis. Okay, so you will get a better route so that the allocation from this cell is removed. Okay, suppose for the time being I give you allocation say 10. Okay, since availability and requirement is satisfied at the same time, 10, 10, and 10. Okay, in this case we are not allocating anything to M. That's okay, so it will not play any role. Suppose we consider a case when we have an allocation that we are transporting initially to M. Okay, let me take this case. Suppose I put a constraint that source 1 does not transport anything to destination 1. So, okay, 3, 4, say 6, we take 5, 2, 3, 2. Okay, again I have 20, 20, 10, 15, 10. Suppose this is a transportation problem and I say source 1 does not transport anything to destination 1. So what happens in this case, I will put the cost of first cell as m, and now I will make the allocations. So what are my allocations? So if I use the northwest corner rule, so I'm transporting 10 units here. Okay, so availability of this destination is exhausted. 10 units here and 5 units here, 15 and 10, 10, 20, 30, 35. Okay, then I have to take this also as 15 just to make this as a balanced transportation problem, because total availability has to be equal to total requirement, and then remaining 50 units I'm transporting here. So now you see this is the total availability and requirements have been exhausted. Now to calculate ui and vj, so I have u1, u2, v1, v2, v3. Suppose I am taking u1 equal to 0 in this case, because this is a basic cell and I do not want anything here, so I put the cost capital M in this case. So what is my v1 is capital M. So what is v2 as 5, and for u2 as -2, and v3 as 4. These are my ui's and vj's. So what is my zij minus eij's for non-basic cell is this 0 plus 4 minus 6 is -2, and this is m minus 2 minus 2, this is m minus 4. Now you see m is a very large number, so this is a positive quantity here, so that means the optimality is not declared. So we have to enter this cell into the basis, because this is the only cell where we have positive zij minus eij. Okay, because m is a
Sir, we have,
large number.
sir, we have to take capital M as positive for minimization case, no?
In every case, capital M is a large number. M is a positive
No,
number. Always M is a
अगर
positive
मान
number. Okay, so we enter this cell into the basis. So what we have is that we have to make a loop in this case. So we enter positive, negative, positive, negative. You see, you take the minimum ratio, again minimum of the negatively marked cell. So minimum occurs at 5. So 5 units are still left. Again, you have to follow this procedure until this m is goes out of the basis. If m does not go out of the basis and optimality declared, then we say that in this case the transportation problem has no solution, which will not occur in this case, I suppose. So I want you to try this at home. Okay, so 5 units will be shifted here, 5 is still left. This is the 2 cell goes out of the basis. You have to recalculate zij minus cj and see what happens. Okay, next is second case is my when source 1, say source I, transport to destination j exactly alpha units. So how to handle that condition? So consider the problem. So source 1, destination 1, 2, 3. Now suppose source 1 supplies to destination 2 exactly say 5 units. Suppose the availability is 20, 30, and then here again 20, 15 and 15. So total sum is 50, total sum is 50 here. Now what we have to do is, since source 1 want to transport exactly 5 units here, so that means there is, because in the algorithm we are looking for the best schedule, but we have if we have already reserved 5 units for source 1 to destination 2, so then there is nothing to plan here. So what we do in this case, we subtract 5 units here, so we are left with 15, and subtract 5 units here and we are left with 10 here. So that means we have already supplied 5 units from source 1 to destination 2. Okay, and we will consider this transportation in the back of your mind, that 5 units have already been transported, that x1 2 is already 5 we have given here, right? in what happens in the rest of the table, since we want to transport exactly 5 units and no more units. So what we do after making this transformation, we will block this route. Now what will happen if we are giving a heavy cost here? That means now no more transportation will be done from source 1 to destination 1, and you solve the problem in the usual way. And in the final answer, whatever solution you get, okay, so whatever is the cost initial, suppose before m initially my cost is say 3 4 6 2 1 5, right? So after you are shifting 5 units from source 1 to destination 1, you are scratching this 5 and taking m. In the final answer, you multiplied 5 into 4 equal to 20. You add 20 units into the final answer. Okay, because that is the cost of transportation from source 1 to destination 2. Okay, and in that case you will see you will not have any more transportation from source 1 to destination 1, only 5 units, that's it. And then you solve the problem. Okay, and any query for this case?
सर जो इससे पिछले वाला केस था वो कौन सा था, मतलब मिनिमाइजेशन था ना वो तो?
सारे केसेस में मिनिमाइजेशन के लिए ले रहा हूं. इवन इफ यू टेक मैक्सिमाइजेशन केस, इन दैट केस, in the previous case, if problem is maximization, so how do you handle that? You assign minus m there. Okay, but m is itself a positive number, then you give minus m to that cell. Okay, clear? Just as we were doing in case of the Bigam method. Okay, so second case is when we are supplying exactly alpha units, and the third case is like when we are supplying at least say source I to destination J at least say beta units if we are supplying. Now how to handle this situation? This is a very tricky case. What you do in this case, consider a transportation problem with 2 sources and say 3 destinations. So again 3 2 2 1 4 7 is suppose my cost of transportation, and this. Okay, and suppose this is my destination 1 2 and 3, and suppose availability is again 20 and requirement is again 15 10 15. Okay, suppose my condition is that source 2 to destination say 2 supply at least 5 units. Now the question is how we can make sure that 5 units are transported from source 2 to destination 2, because when we are solving the problem with my UI VJ method or the optimal the simplex method, we cannot make sure that 5 units are left in the end here, because what we are doing, we are following the ZJ minus EJ rule and the minimum ratio rule. So it is possibility that by chance you have more than 10 units left at this place, but it is not always the case. But how will you train your algorithm that you will always get at least 5 units here? Okay, unlike in the previous case when I had to make exactly 5 units, so what I did, I subtracted the availability and requirement, the 5 units, that made me sure that 5 units are being transported, and then I blocked the route. So that means no more transportation is being done. But this is a different case. We have to make sure that 5 units are gone there, and then the route is still open. More amount can also go, so 5 has to go. So what we do in this case, because source 2 to destination 2 we have to send 5 units, so what we are doing in this case is we are splitting this problem into in this way. So what I'm doing is I am converting this 2 source 3 destination problem to 3 source 3 destination problem. I call it as S2 dash. Okay, so this is destination 1, destination 2, destination 3. Now what I want is that source 2 must supply destination 2 5 units. Any hints from your side? Anybody want to give how to handle? Okay, so what I'm going to do is I am splitting this 20 unit as 5 and 15. Okay, so what I'm going to do here is I'm going to block these routes. So that means 5 units is transported to this place from source 2 to destination 2, and I will keep open rest of the routes. So this cost is 4, and then this is 3, 2, 2. So what happens, this source 2 case is being split up into two cases, where I have put divided this availability of 20 units into 5 and 15. And for 5 units I have opened only this route, so this will make sure that 5 units are going to this destination. By opening the same route in the bottom line also will give you the possibility that more amount can be transported in this unit. And finally you can club the answers of these two sources together to get the final answer. So this will make sure that at least 5 units are being transported to this case, and you can transport more amount also. Okay, so then again you solve go by the usual um, say least cost method, or the northwest corner rule, or Vogel's method, whatever initial solution you find, and then go for UIs and V's and find the optimal solution in this case. And certainly in this case you will have 5 units transported here in this case, because other two routes of this source are blocked. Okay, so any queries so far? Anybody has any query, please tell me.
Sir, can you explain it once again?
Which part?
सर जो आपने सर ये जो 2 आपने लिया कैसे लिया एक बार वो बता दीजिए.
जो दो, क्योंकि ये 20 यूनिट्स हमें ट्रांसपोर्ट करने हैं, राइट, और हम चाहते हैं कि
Yes,
कम से
sir.
कम 5 यूनिट यहाँ जाए, पर वो कैसे हम उस बात को श्योर करें कि 5 यहाँ जाएं? तो हमने क्या किया, सोर्स की अवेलेबिलिटी को दो हिस्सों में डिवाइड कर दिया, 5 और 15 में। तो 5 और 15 करने से क्या हुआ कि जो सोर्स 1 टू डेस्टिनेशन 1 वाला लिंक है और सोर्स 1 टू डेस्टिनेशन 3 वाला लिंक मैंने ब्लॉक कर दिया। तो ये सेकंड सोर्स इन द सेकंड रो विल ट्रांसपोर्ट दिस 5 यूनिट्स टू वेयर, एट दिस प्लेस ओनली, और कोई रास्ता ही नहीं है इसके पास ट्रांसपोर्ट करने का। हाँ, और जो बॉटम वाली सोर्स है, जो कि सेकंड सोर्स का ही बचा हुआ हिस्सा है, वहां पर पॉसिबिलिटी है कि ये 15 यूनिट इस जगह पे भी आ सकते हैं, नहीं भी आ सकते, बट ओवरऑल मैंने सोर्स 2 टू डेस्टिनेशन 2 पे 5 तो दे ही दिए ना। So this is the only way that we keep open this route. Okay. Is this clear? चलें आगे फिर, if there is no query. Okay, so this was all about my transportation problem. And one more thing I wanted to discuss in the maximization case, that we had used this, we have reversed the optimality criteria. Other way is convert this problem to minimization. So how you are going to convert this problem to minimization? That select the largest element in the cell in the cost matrix and subtract every other element from this largest element. The resulting matrix will be, the resulting problem will be a minimization type problem. So for this case, as an example, to convert to minimization, so what we are doing is you select the largest element as 6, so subtract every element from 6, so what will you get is this. So 6 minus 3 is 3, 6 minus 4 is 2, 6 minus 5 is 1, 6 minus 3 is 3, 6 minus 2 is 4, and this is 0. So this is a minimization minimization type problem. So once you have converted this problem to minimization type, now you can solve it with the usual way of the minimization type, and then in the final answer, you put the allocation into the original matrix, you will get the answer for the maximization type problem. Okay. So there are two ways to handle maximization type problem. Either you reverse the criteria of Zj minus Cj, or you convert this problem to minimization type problem. Is this fine? Am I audible? Hello?
वो 2 आएगा ना, ऊपर 2 आएगा ना, मतलब वहां पर जो सबसे पहला कॉलम है जहाँ पे 3 लिखा हुआ है।
हाँ, तो
हाँ
2
यहाँ
क्यों
पर
आएगा? तो लार्जेस्ट एलिमेंट क्या है? 6। तो 6 में से 3 माइनस करेंगे तो 3 आएगा ना।
नहीं, ऊपर 2 लिखा था आपने मेरे ख्याल से पहले।
कहाँ पर पहले?
कोई
ये
नहीं, ठीक है।
3 दिख रहा है मुझे तो यहाँ। 3, 4, 5. Okay, so you subtract every element from 6 and you convert this problem to minimization type. Okay, fine. So okay, then we move further. So this was all about the